Good morning and good afternoon. Thank you all again for joining us today. Before we get started, I just want to go over how the Q&A session will take place. Many of you may already be familiar with this, but after the presentation, we will have time for a brief Q&A session. During the presentation, please feel free to chat in your questions. Make sure to be chatting to host, presenter, and panelists. I'll be keeping a parking lot of all the questions, and we will address them in the order they came in, and as many as time allows. Any questions that are not addressed during the time of this webinar will be addressed at a later time offline. So please feel free to submit any and all questions. So without further ado, I will turn this over to our presenter today, Dr. Felix Elwert.
Good afternoon, everybody. Welcome to this. Thank you for joining us for this introduction to working with directed acyclic graphs. Okay, so I'm going to advance the slides now. This presentation is based on two papers that you can find on my website. The first is an introduction to graphical causal models, mostly for the social sciences, but also for the biomedical sciences. The second paper contains a number of real-world examples, some of which, if time allows, we will get to as well today. So what's a directed acyclic graph? This here is a directed acyclic graph. The directed acyclic graph is a means to notate causal assumptions about the data generating process and then to work some fairly advanced problems in causal inference using a purely graphical syntax. Directed acyclic graphs were chiefly developed by a computer scientist named Judea Pearl starting in the late 1980s, and they've become very successful, not just in computer science, but also in epidemiology and other social sciences. DAGs have origins in structural equation models. As you can tell, they look very much like conventional linear path models, if you've seen them before, but they also have origins in Bayesian networks, and thus they're much more general than conventional linear path models. Important for our purposes is that directed acyclic graphs, or DAGs, are fully compatible with the potential outcomes framework of causality. And that's important because the potential outcomes framework to causality is currently the reigning framework for causal inference in the biomedical and social sciences. So we are simply going to learn new syntax, a new notation to work within that same framework. So what are they good for? We're going to start with a premise here, and the premise is that all causal claims about reality, all causal claims that we draw from data about reality are relative to an assumed data-generating process. That is, they're relative to our theory of how the world has generated the data. This is a fact. Now, DAGs help with causal inference in four ways. They help with causal inference because, first of all, DAGs graphically notate the causal assumptions about the data-generating process that all of our causal statements are relative to. Second, we can use simple rules to link these causal assumptions to the statistical associations that we could potentially see in the data. So DAGs help us in step 2 to connect our theory about how the world works to what we can actually see in the data. Now, once we've done that, we're in the third step where we can use DAGs to perform what is known as identification analysis. Now, we'll define what that means later. Briefly, identification analysis tells us whether or not any statistical associations that we can see in data, associations such as regression coefficients, for example, do have a causal interpretation given our data-generating theory. And then finally, DAGs are really helpful because they can inform key statistical topics such as matching, regression, instrumental variables, mediation, missing values, and so forth. This fourth use of DAGs we will cover in our second session, I believe, in 2 weeks. Good. So with that, let's go through this list of to-dos one by one. We're going to start by meeting the elements of DAGs and their interpretation in order to notate the data generating process. So, first and foremost, DAGs are pictures that encode the analyst's causal or structural assumptions about the data generating process. In other words, a DAG is a picture of how you, the analyst, believes that the world works. DAGs consist of three elements. First, DAGs obviously contain letters. We call them nodes or vertices as well. These letters represent variables which may be observed or unobserved. Second, DAGs consist of arrows. Arrows represent direct causal effects. So having an arrow from T to C means that we believe that changing T will cause a change in C. And finally, third, DAGs consist of missing arrows. Missing arrows represent exclusion restrictions. That means a missing arrow indicates that we believe that there is no direct causal effect from one variable to the other. Specifically, a missing arrow from T to Y indicates that we believe that T does not directly cause Y through any mechanism other than through C. It turns out that the missing arrows are where all the action is in a DAG. The missing arrows are the key ingredients. In the language of economics, missing arrows represent exclusion restrictions. That is, they represent the exclusion that one variable does not cause the other. Now, for deeper technical reasons that I won't get into, it's really these absent arrows, the missing arrows, that represent the assumptions on which our causal inferences will rest. Hence, in drawing DAGs, it is the missing arrows that we need to pay particular attention to, that we need to be particularly careful to justify. Without missing arrows, without exclusions, there can be no identification of any causal information from data. Now, let me illustrate this with a toy example from smoking research. So this is the same DAG as we have had, as we've just looked at. And this DAG might capture the following qualitative causal statements about the data generating process. The error from T to C might mean that smoking causes cancer. So T is smoking, C is cancer. Smoking causes cancer. The second arrow shows that cancer causes mortality. Y is mortality. Now, furthermore, we have an exclusion restriction here because so something is wrong here on my end. Anyway, it's stuttering. I hope that you can still hear me. So note that we have no arrow from T to Y. That means we're asserting that smoking does not directly cause mortality. It only causes mortality via cancer. And if X represents low socioeconomic status, then these three arrows that emanate from X would signify that low socioeconomic status causes smoking, cancer, and mortality. And finally, we might have a variable that we call U, which might be perhaps unobserved childhood insults to health. And here, this DAG claims that childhood insults to health cause low socioeconomic status and mortality, but not directly smoking or cancer. So here you have a fairly complicated causal story about how the world works. And now you might, if you believe that the world works like this, then you can now use this graphical notation to derive what you might see in data and to discern whether you can identify the causal effect of smoking on cancer and or mortality. But be warned, if you do not believe that my little story here represents how the world truly works, then you have no reason to believe anything that I say from now on. Or perhaps spoken less hyperbolically, remember that all causal statements that we derive from data are relative, are conditioned on an assumption about the data generating process. The DAG represents our beliefs about the data generating process. And if you and I don't share the same beliefs about how the data have been generated, how the world works, then we will not come to the same conclusions about what the data do or do not mean. Thus, if you do not believe this DGP, then you must change it, then you must change the DAG. For illustrative purposes, of course, now I'm just going to assume that we believe this DAG. So, now let me say a few formal things about DAGs. First, DAGs are very general tools. DAGs are nonparametric. Oh, there's a typo. They're nonparametric in two senses. They're nonparametric in the sense that DAGs make no distributional assumptions about the variables. That is, this graph here could represent normally distributed variables, Bernoulli variables. Really, any distribution goes, we don't care. So that makes them very, very general. Second, the DAG makes no functional form assumptions about the causal effects. That is, the effect of, say, the degree of low socioeconomic status on smoking could be a linear probability relationship. It could be linear on the odds ratio scale. It could be discontinuous. It could be jumpy. We really don't care. The syntax that we're using here is agnostic as to distributional and functional form assumptions. And in that sense, DAGs are a great generalization of more conventional approaches to structural equation modeling. So DAGs are nonparametric. Good. Now we're going to introduce some elements of DAGs in order to work with them. First, we want to define the notion of a path. The formal definition of a path is that a path between two variables is a non-self-intersecting sequence of adjacent arrows. And that's, highfalutin text speak for saying that a path is what you think a path really is. A path, say from X to Y, might be the sequence X, T, Y. It might also be the sequence X, T, U, Y. So an important point about paths here is that paths can go backwards or forwards in an arrow. Again, X, T, Y is a path, but X, T, U, Y is also a path, even though the latter traveled against the distance of an arrow. So that's a path. We like paths because paths are possible conduits, transmitters of association. Now we're going to differentiate between causal paths and non-causal paths between a treatment and an outcome. So suppose that T is our treatment and Y is our outcome. A causal path from treatment to outcome is a path in which all arrows point away from treatment and toward the outcome. In this DAG, there's only one causal path from T to Y, and that is the direct arrow from T to y. This one here. Here. Okay. So that's the single causal path from T to Y. Causal paths are important because causal paths transmit the causal effect. And you may have multiple causal paths between treatment and outcome, and the total set of all causal paths comprises the total causal effect. I hope that's intuitive. Now, by contrast, non-causal paths are defined as paths between treatment and outcome in which at least one arrow points against the flow of time. So revisiting our example, there's a path from T to X to Y. But because that path forces you to travel against the direction of the arrow from T to X, this is a non-causal path. This terminology makes sense because we know that causality flows in time. A cause has to precede its effect. Hence, if you're going against the direction of the arrow, you're engaging in time travel, and time travel isn't real. So any path that forces you to travel against the arrow of time is a non-causal path. So we've seen one non-causal path from treatment to outcome with T, X, Y. And there's a second non-causal path between treatment and outcome that goes from T to U to Y. This path as well is non-causal because, again, it travels against the arrow of time from T to U. That's causal and non-causal paths. The point about paths is that causal paths transmit the causal effect that you're interested in, and non-causal paths may transmit spurious associations or bias that you want to get rid of. Now, there's a certain type of variable in DAGs that plays an outsized role in understanding DAGs, and these are so-called collider variables. A collider variable is a variable into which two arrows point along a path. This sentence reads funny, but every element in it matters. A collider variable is a variable into which two arrows point along a path. So first of all, a collider variable clearly is a variable in which two arrowheads collide. But secondly, a collider is always defined with respect to a specific path. So now let's look at the variable T. T is a collider on the path from X to T to U. It's a collider on this path because two arrowheads collide in T on the path from X to T to U. But now let's look at a different path. On the path from X to T to Y, T is not a collider because on that path, the arrow goes into T and it peacefully leaves on the other side. So on X to T to Y, T is not a collider. If I'd had to guess, I'd say that misidentifying variables as colliders or non-colliders is one of the key sources of mistakes in working with DAGs. So please be mindful that colliders are always defined with respect to a specific path. And in this DAG here, T is a collider on one path, but not on another. Now, with this, more or less, we've vested these pretty pictures with all the meaning that we need in order to interpret the DAGs as nonparametric structural equation models. In other words, graphs are equivalent to structural equations with no loss of information. So here I've given you two different interpretations, algebraic interpretations of the DAG. If you wanted to make the assumption that every arrow in this DAG represents a homogeneous and linear relationship, that is a conventional linear path model, then you would interpret this DAG as Sewell Wright would have in 1921. So our DAG would be exactly equivalent to this linear system of equations. But you remember that we didn't actually make any functional form assumptions, which is why today we interpret DAGs as non-parametric structural equation models following Pearl 1995. And non-parametric structural equation models really are purely qualitative. So let's look, for example, at the equation for the variable C. This equation says that C has been generated or caused by some idiosyncratic function f of C that may vary across individuals I, and that takes as arguments T, X, and an idiosyncratic error term on C, which we usually don't draw. So by comparing the algebra with the graph, you can see that they're one-to-one equivalent. The graph tells you for every variable the direct causes of that variable. So here in the case of the variable C, the graph tells you that T, X, and E of C have direct errors into C, so that are the causes. And the algebra tells you the exact same thing. C is caused by T, X, and EC. And at this point, it's purely a matter of your personal preference if you prefer to work with a pretty picture or with a big system of nonparametric structural equations. But syntactically and semantically, they're equivalent. Okay, so the takeaway point so far, we're concluding section 1 now. The takeaway point was that we can use DAGs to encode our qualitative causal assumptions about the data generating process. And in doing so, we're really just drawing a picture of nonparametric structural equations. Now I would like to move on. This is probably the key section of our presentation today. Now that we have encoded our causal assumptions about how the world works, we want to know what associations our model would imply in the data. In other words, if we're willing to assume that our graph accurately represents the data generating process, we now ask, well, if this is true, then what associations should I see in the data? Now, I will do this twice. On this slide, on slide 14, I'm summarizing the process that we're going to go through later in some detail. The claim is this. The claim is that simple rules connect the causal assumptions in the DAG to the statistical associations that you might pick up in the data. Indeed, there's a rule called D-separation that helps you derive all implied associations and independencies. And it's really just a three-step. First, we note that we have an axiom here that says that the causal effects in the graph give rise to observable associations in the data. So it's this first statement that does the key work of connecting our theory to what we can see in data. Second, we note that all associations travel along paths, but not all paths transmit associations. Thus, so in fact, only open paths transmit associations, while closed paths do not. So what's left for us to do then is to learn the rules that help us distinguish between paths that are open or closed. Now, once we've done that, we can move on to identification analysis and ask whether an observed association equals or identifies the causal effect of interest. Okay, so let's go through this. It turns out that all marginal and conditional associations in data originate from just three causal structures. The first two are well known, the third is not. First, if A directly or indirectly causes B, then they're going to be associated. So direct or indirect causation implies association. Second, A and B are going to be associated even if they don't cause each other, if A and B share a common cause. This is the causal structure of confounding. So A and B are going to be associated if they share a common cause. Third comes a rule that's less well known and that's actually kind of hard to get intuition for. Two variables, A and B, that don't cause each other and don't share a common cause will become associated if we condition on their common effect. Since this and this is the structure of selection bias or endogenous selection bias. And because this third rule is harder to understand, I want to spend some quality time with it explaining it. So here the claim for the third rule was that. Consider this DAG here. In this DAG, we're saying we believe that the world works in a way that A and B don't cause each other and don't share a common cause. Therefore, A and B are marginally independent. There's no association between them. The claim is now that if we condition on the common effect, C, and we're going to induce an association between A and B where no association existed before. So conditioning on a common effect creates a conditional dependence between marginally independent variables. Now, if you wanted to say that A is the cause and B is the outcome, then the true causal effect of A and B would clearly be 0. But the conditional association between A and B given C is non-zero and hence biased for the true causal effect of A on B. Again, this is the structure of selection bias. And you'll note here, while we've spent time defining a collider before, a common effect of two variables is always a collider between these two variables. And the fact here is that conditioning on a collider will induce an association between its immediate causes. Let me give you two substantive examples for this. The first is an example by Judea Pearl. It's a famous, it's the canonic sprinkler example, if you can believe it. So, we're interested in the process that makes my front lawn wet. So let C be a binary variable. It's equal to 1 if the lawn's currently getting wet. It's 0 if the lawn's not getting wet. There are only two ways that the lawn can get wet. It could get wet because it rains, or it could get wet because my sprinkler is on. Now, my sprinkler is on a random timer. It's just because this is how I roll. This is how I've set up the example. Now, because the sprinkler is on a random timer, that means that there are no systematic inputs into B. Hence, A and B share no common causes, and they don't cause each other. So now ask yourself, if you know that it is raining, so if you know A, can you infer something about B? The answer is no. The sprinkler is on a random timer. Knowing that it rains or not tells you nothing about whether the sprinkler is on. But now let's condition on C. Now let's look only at those moments where the lawn is actually getting wet. If I'm telling you that it's not currently raining, but you do know that the lawn is getting wet, then that immediately implies that my sprinkler must be on. So what's happened is that because you've conditioned on the common effect C, you've induced an association between A and B, where association simply means that knowing the value of A tells you something about the value of B for at least one level of A. Again, knowing that the lawn is currently getting wet and being told that it's not raining immediately tells you that the sprinkler is on. So here you've been able to infer something from A to B that you weren't able to infer before without knowing C. So this just illustrates the process of endogenous selection. A second example may be, let's use a Hollywood success example. Suppose there's only two ways that somebody could become a famous Hollywood actor: having great acting skills or looking really, really beautiful. Now, suppose, just by setup of the example here, that good looks and acting skills are independent in the population of budding actors, right? Whether somebody's good looking tells you nothing about whether they're a good actor and vice versa. So good looks and acting skills are marginally independent if you know nothing else. But what if we condition on the common effect? What if we only look at the population of famous Hollywood actors? Well, then knowing that somebody cannot act tells us that they must be really great to look at. Or conversely, knowing that they're really painful to look at tells us that they must be great actors. So again, having conditioned on a collider has induced an association between its immediate causes. Now, a while ago I said that there's exactly 3 rules that connect causation to association. Those rules were causation, confounding, and conditioning on a collider, that is selection. Now I'm going to give you rule 3.5. It turns out that conditioning on a descendant of a collider is qualitatively the same as conditioning on the collider itself. So we already know that conditioning on C will induce an association between A and B, but conditioning on D will also induce an association between A and B. The intuition here is that you can think of D as a noisy measure of the true underlying C. So clearly conditioning on D will not induce the same association as conditioning on C itself, but it's going to get there very closely. Now, these 3 sources of association in causal analysis are immediately translated into 3 sources of bias when we're trying to estimate the causal effect of A and B. And indeed, I would claim that these 3 sources of bias are the only structural sources of bias in causal analysis. Thus, if we want to understand bias in causal analysis, we first of all, and exclusively really, need to understand these 3 sources of bias. So here we go. Suppose that A is the treatment and B is the outcome. And we're interested in estimating the causal effect of A on B. Overcontrol bias exists if you're controlling for an intermediate variable. We call this overcontrol bias. Controlling for C will break the path here, if you will. It'll stop the flow of causation from A to B. Controlling for C, or conditioning for C, will control away the very causal effect that you're interested in. Hence the general rule that we should never control for an intermediate variable. The second source of bias is confounding. Confounding results from failure to condition on a common cause. This should be intuitive. If A is the cause and B is the outcome, then by this causal model, A does not actually cause B. Nonetheless, they're going to be associated because they share a common cause. Hence, if you controlled for C, you would eliminate that association. And if you don't control for C, this spurious association would remain and you'd get confounding bias. So confounding bias results from failure to condition on a common cause. And third, endogenous selection bias results from mistaken conditioning on a common effect. In that sense, confounding and selection are really polar opposites of each other. They result from different causal structures and from different actions, and they have different remedies. Confounding results from a common cause. selection results from a common effect. Confounding results from failing to control, and selection results from controlling. The solution to confounding is to control, and the solution to selection is not to control. So it's kind of unfortunate that in parts of the social sciences, people use the words confounding and selection interchangeably, but from a causal perspective, they're really different things. So the beauty is that all DAGs can be built from these three structures. All DAGs, however complicated your data generating model is, your model is going to be built of causal chains, forks, and inverted forks. And because we have just learned the associational implications of these three elementary causal structures, we now can put these structures together artfully in order to understand the associational implications of arbitrarily complicated causal models, even a model that's as ugly as this DAG here. So the famous D-separation criterion merely puts together the three rules that we've learned in order to determine whether a path is open or closed. Whether or not a path is open or closed depends on whether we do or do not condition on a collider variable. And it can be expressed in non-technical language using just three rules. The first rule is a blocking rule. It says that conditioning on a non-collider anywhere on the path blocks the path. Second, not conditioning on a collider blocks the path. Then the obverse of this is the opening rule. It says that not conditioning on any non-colliders and conditioning on all colliders opens a path. If you read my 2013 article, you'll see how what we've just discussed with these three elementary causal structures neatly translates into the rules on this slide 21. So we've not introduced any new information here, we've just put things together. Okay, so this is kind of cool. Now you can take an arbitrarily complicated causal model, such as the one on this slide here, and ask, if this is how the world really works, what marginal and conditional associations and independencies should I be able to see in the data? And it turns out that even this simple model has about 180 of those implications. This is really cool because you can now test all of these implications one by one. And we should really do that in practice because we know that our causal inferences are conditional on the assumption that our DAG here is in fact true. So the DAG, by the rules of association, tells us immediately to what extent and how we can test our assumptions. Now we're in the last part of the presentation. Now we're doing identification analysis. So what's identification? We say that the causal effect of T on Y is identified if it is possible, with ideal data on observable variables, to purge all non-causal associations from the observed association between treatment and outcome, such that only the causal association remains. Let me say that again. Identification means that we determine that we can get rid of all spurious association such that we can isolate the causal part of our statistical association. And the nice thing is that we can use DAGs in order to make this happen. There are many ways to use DAGs for identification analysis, and arguably the most important one in practice is the so-called adjustment criterion that was proved by Ilya Spitzer and colleagues 2010. Remember, identification on the previous slide here means that we can get rid of all the spurious association so that we're left with only the causal association. So in a DAG, this means that the total causal effect of treatment and outcome is identified by adjustment. If you can condition on a set of variables that block all non-causal paths between treatment and outcome and do not block any of the causal paths between treatment and outcome. So let's look at this a little bit. The first rule says block all non-causal paths. Why would you do that? Well, because non-causal paths are carrier of spurious association. So you want to block all biasing paths. Good. Second, you're interested in the causal effect. Therefore, you shouldn't block the causal effect. That's it. The beauty of this criterion is that it underlines all causal claims rendered from regression and matching analyses. In other words, this is the identification criterion that underlies, I would hazard a guess, of at least 95% of all causal claims in the empirical sciences. Now, there are other ways to get to identification, but adjustment, so simply throwing in control variables, is certainly the most important one. So let's apply this now. So here you remember this graph because I leveled, perhaps overly simplistic smoking story onto this. T is smoking, C is cancer, Y is mortality, X is socioeconomic status, and U is childhood health. So now we're asking, can we identify the total causal effect of T on Y by adjustment if U is unobserved? Again, you're interested in the total causal effect of smoking on mortality in a world where you observe X, T, C, and Y, but not U. So the answer is that simply applying the rules that we've just learned, the answer is yes, you can. There are 4 non-causal paths from T to Y. Actually, sorry, let me restate the adjustment rule. The adjustment rule says that the causal effect of T on Y is identifiable if you can block all non-causal paths without blocking any of the causal paths. So what are the causal and non-causal paths? Well, there's one causal path, T to C to Y, and we don't want to block that. And then there are 4 non-causal paths, T to X to U to Y, T to X to Y, T to C to X to Y, and T to C to X to U to Y. So there are 4 non-causal paths. You'll note that all 4 of these non-causal paths pass through X. And X is a non-collider on all of these paths. Now, if you recall from a few slides before, conditioning on a non-collider blocks a path. Therefore, conditioning on X blocks all non-causal paths from T to Y. Hence, conditioning on X, you've blocked all non-causal paths, you've gotten rid of all spurious associations, but you've not blocked any causal path. Therefore, the conditional association between T and Y given X gives you the causal effect of T on Y. Now we could ask a different question of the same DAG. We could ask, can we identify the total causal effect of X on Y if U is unobserved? Now here you'll note that there are 3 causal paths from X to Y, X to Y, X to C to Y, and X to T to C to Y. And these together give us the total causal effect. And then there's one non-causal path from X to Y. That path is X, U, Y. Can you identify its causal effect? No, you cannot. Since U is unobserved, we cannot condition on U to block the path. Oh, sorry, I forgot to say. So note that the non-causal path goes via U. This non-causal path is open because U is a non-collider. Hence, there flows spurious association from X to Y. We would like to block this path by conditioning on U, but we cannot condition on U since U is unobserved. Hence, The observed association between X and Y now is a mixture of, on the one hand, the total causal effect of X and Y, and the non-causal association via the open non-causal path. In other words, the association between X and Y is biased for the total causal effect. Now, applying these rules takes a little practice, but it's really quite helpful to go through a bunch by hand. Here I've given you an example that we cannot do in this presentation here because this is a really hard example. If you're taking notes, I'm just going to tell you the answer here is that you cannot identify the causal effect of T on Y, but it's actually kind of tricky to show why you cannot identify this effect. So, okay, so that was it for the introduction. I want to give you just perhaps one example here of how you can use these insights about DAGs and colliders in order to make sense of one kind of fun study that that went awry. This is not a smoking study, but perhaps you might enjoy it anyway. So the point here is that we've written a paper and others have written papers that give lots of real practical examples, real examples for how conditioning on a collider can induce selection bias. So here I want to give you one story. This is a story where where researchers ask what determines whether a rock and roll album makes it into the Rolling Stone magazine's list of the 500 greatest rock and roll albums of all time. And one theory is that topping the Billboard charts should increase the chance of making it into the Rolling Stone 500 greatest albums list. The theory here is that the Rolling Stone editors cannot know all rock and roll albums, but they certainly know every album that has topped the Billboard charts, and hence topping the Billboard charts should increase the chance of winning the Rolling Stones 500. But a number of studies have found a dramatic and counterintuitive negative effect of chart topping on inclusion in this list. So the authors now have two choices. They could post hoc a theory about how perhaps the Rolling Stone editors are really snooty and they penalize albums that have been commercially successful. Or they could say, we don't believe this, maybe something went wrong. And yet, fortunately, these published papers did include footnotes that said, oh, something must have gone wrong, and I will explain to you what went wrong. What went wrong here is sample collection. The authors were not able to collect data on all rock and roll albums ever released. Okay, that's tens of thousands of albums, nobody has data on them. So instead, they compared the most successful to slightly less successful albums. They sampled from the population of all albums by the following rule. If you've been included in the Rolling Stone 500, you're included in the sample. And if you've topped the Billboard chart, then you're included in the sample. So the sample now includes all 500 albums, Rolling Stone albums, plus 1,100 albums that have received other prizes. And now here comes the kicker. Of course, we're only analyzing the data that we actually have in our sample. That is, we're conditioning on the fact that we're analyzing the sample, like everybody does. But note that sample inclusion is a collider between the treatment and the outcome. And conditioning on a collider induces an association between its immediate causes. Thus, we now have two sources of association between Billboard chart topping and winning in the Rolling Stone list in this sample. The first source of association is the likely positive causal effect of Billboard chart topping on Rolling Stone inclusion. The second source of association is this artifact, is this spurious association that was induced by conditioning on the collider. And that association is strictly negative. Specifically, if you know that an album is in the sample, even though it did not win the Rolling Stone 500, well, then it must have won the Billboard. Conversely, if an album's in the sample but did not win the Billboard, well, then it must have won the Rolling Stone, because otherwise it wouldn't have been in the sample. Hence, we have a strong and strictly negative association induced by our sample selection criteria. The observational epidemiologists amongst you will note that this study here follows a severely flawed case control design, where we've sampled not just cases, that is those who've won the Rolling Stone, but we've also sampled as a function of the treatment, which is a big no-no in case control analysis. Okay. So here this is a simple graph that highlights this problem. Now, I see that we have 5 minutes left. I want to close by saying that the purpose of today's presentation, here we go, was to introduce the main uses of DAGs. First, we learned to use DAGs to graphically notate the causal assumptions about the data generating process. Then, we used DAGs to move from causal assumptions to associations that you should be able to see in the data if your assumptions are true. Then, we used our ability to derive associational implications to determine which associations are actually causal, that is, which associations identify a causal effect. And then we've begun to talk about how this is useful for informing actual real-life analyses. In our next session, we're going to discuss some real examples from tobacco control research, looking at examples of neonatal tobacco-induced mortality and tobacco control through taxation using various statistical tricks, which we'll explain using DAGs. With that, I want to close and give you an opportunity to ask some questions.
Thank you for that great presentation. I know it's a lot to take in, so we're going to give a few moments for people to submit in any questions that they may have. And they're coming in. But while they come in, if we can just share some information for next session.
So, okay. So there's already a question. Should I answer that?
We'll get there in one moment. I just want to see if any others come in so we have a few we can get to at the same time. But just for everyone's information, the next session will be February 22nd, same time, 1 to 2. And the presentation is entitled Using DAGs to Interpret Inference and Causation Applied to Real-World Tobacco Regulatory Science Examples. Registration is open, so please make sure to register, and we hope you'll join for that next session. So now let's look at what questions have come through.
Yeah. So, all right. So Andrea is asking, can you provide some practical tips on how to use DAGs in designing a study or planning analyses? Yeah, that's a great question. I think this is a good use of DAGs. So for planning a study. So one thing, using just the tricks that we've introduced today, what you can do is you can, first sit down and write out a DAG for how you think that your particular subject matter domain works. In that, so you would write out the DAG for your particular problem. Now, what's really important when you write out this DAG is that you need to keep in mind that you need to include all common causes, whether they are observed or unobserved. It is critically important not to forget the unmeasured variables. Then once you've written out how you think the world works, you can use, for example, the adjustment criterion to ask what sets of variables you need to control for in order to identify your causal effect through just regression analysis. And in that process, you'll discover that often multiple adjustment sets will identify the causal effect of interest. And then you could look at these different feasible adjustment sets and ask which one is cheapest to collect. Some adjustment sets will be impossible to collect, so you can't do it. Other adjustment sets will be really prohibitively expensive, so you won't do it, but others might be feasible and cheap. And so the DAG will tell you which variables you have to control, the DAG will tell you which variables to collect and then control Okay, next. So there are more. I could say more on this, but I'm going to move on.
The next question is, if we do not have all the samples possible in the universe, or don't know if we do, how can we know that we do not have a bias?
Okay, so I believe the question was meant to say, what if we do not have all possible variables in the universe, or don't know if we have all variables in the causal process? So I want to tell you why I've reformulated the question. So what we've talked about today was not about sampling in the sense of collecting data. It was about identification analysis under the assumption that you have perfect data. And I'm interpreting the word universe here as meaning the DAG, the universe of my data generating process. So the question thus becomes, what if we don't know if we have all variables in the data generating process? Well, unfortunately, the answer here is really dispiriting. If you don't know, or if you're not willing to claim that you understand your data generating process, then you lack the theoretical foundation for making any causal claims from observational data. And this is harsh, but and it's unfortunate, but it's true. It can be proven. If you're not able or willing to convince your audience that your data generating model is to be believed, then we cannot. Then we lack the theory to draw inferences from data. And I should say that this is even true in randomized experiments. In a randomized experiment, we also need to assert a theory about the data generating process. And that theory is that randomization has worked. Now, we can partially test randomization, but we can never fully test randomization. So any causal interpretation of a randomized experiment is conditional on the assumption, the untestable assumption, that randomization has worked. If you're not willing to make that assumption, then you cannot use even randomized experiments to justify causal inference. But of course, randomized experiments are loved because the theory that you need here is fairly low level. However, in most observational studies, it's usually a lot harder to assert that you have all the variables that you need. Thank you.
And that is all the time we have today. So I want to thank our presenter again, and thank you all for your questions and for joining us for this session. We hope you will join us again on February 22nd for the follow-up on DAGs. Just as a quick note, there will be poll questions that you should see. If you could please complete those, we would love your feedback and ideas for webinars moving forward. So thank you all very much, and we hope you'll join us next time. Have a great day.
Thank you, everybody.